plays in many forms, including research partnerships, technology, internships and training programs, joint projects, and funding support. This collaboration allows for the development of innovative products, services, and technologies, and also helps to create a skilled and knowledgeable workforce. Before we begin this session, I invite Professor Mohammed Qasim Yes, Chairperson IEEE Kerala Section and Founding Chair of IEEE Education Society Kerala Chapter, to deliver the welcome address.
Thank you, Neha, and welcome all the participants and our chief guest Sukumar Kamalasadan to this session talk, and really happy to be happy to partner with EDSOC activities, and the reason being as the founder chair of Education Society Kerala chapter and currently the chair of Kerala section, have seen the activities of Education Society chapter has gone up to a remarkable level in a short span of 2 years. Education Society Kerala chapter started in April 2021, and now 2 years has completed, and under the leadership of our CM Varghese, the activities of the society chapter is on the hike, and we were really number one in region 10 Asia Pacific EDSOC chapters, and performing well, and we got recently too many projects awarded to get implement, and I welcome all the participants to this talk. And currently Kerala section, it's globally among 344 sections, we are number 2 globally, and some of our society chapters are excellent. They are performing very well, and to name few of them, the Computer Society of Kerala chapter, which was formed in 1985, currently it is standing globally number 1 and among all the Computer Society chapters, as well as among all the society chapters. And then we have our Power and Energy Society performing extremely well. Then the IEEE PLS Dawn chapter is also doing good. And currently, out of the 15 technical society chapters, nearly 50% of the society chapters are performing extremely well, and the membership of our Kerala section is also very good, in the sense recently we had a dip because of the non-renewal of membership, and it was there globally. Now we are picking up, and we move to position number 2 globally, and I thank all the volunteers and the supporters of and the members of IEEE Kerala section to support the activities of Kerala section and to associate or partnership with Kerala section. And I welcome our chief guest, Dr. Sukumar Kamalasadan, to this talk session on behalf of EDSOC Kerala chapter and on behalf of all the members present for this session. Welcome you, sir, to this meeting. And I welcome our chair, CM Varghese, to this meeting, and I welcome all our office bearers of EDSOC Kerala chapter and the student leadership team volunteers of Kerala chapter to this technical session, and welcome you all once again, and thank you. Thank you, sir.
Thank you, sir. I now invite Engineer CM Varghese, Chairperson of IEEE Education Society Kerala Chapter, to welcome the speaker for the day.
I think my job is to introduce Dr. Sukumar here. And most of the seniors in IEEE, Dr. Sukumar is well known, but for others who are new here, I have to introduce him. Dr. Sukumar Kamalasadan is an IEEE PS Distinguished Lecturer and a Distinguished Scholar and Professor of Electric Power Engineering at the University of North Carolina, Charlotte, and the Director of Power, Energy, and Intelligent System Lab within the Energy Production and Infrastructure Center, EPIC, at UNCC. He received his PhD degree in electrical engineering from the University of Toledo, Ohio in 2004. His research interests include data-driven approaches to power grid modernization, smart grid, microgrid, power system operation and optimization, power system dynamics, stability and control, and renewable energy-based distributed generation. Professor Kamalasadan research for the last 15 years has resulted in tools and methods that have a high level impact on electric utility modernization, with a fleet-wide deployment of his tools that enabled modern grid management and control integrating renewable energy and energy storage. His research work has secured more than $12 million with his direct supervision from the US Department of Energy, National Science Foundation, Siemens Research, Duke Energy Corporation, Schweitzer Engineering Lab, and several other industries. And he is the chief architect of Duke Energy Smart Grid Laboratory at UNCC, a $5 million facility. Authored over 150 papers published in international journals, and he's a paper review chair of and associated editor of IEEE Transactional Industry Applications. With his 25 years academic experience and 7 years industrial experience, he's a recipient of several awards, including the National Science Foundation Faculty Early Career Award in 2008. When ETSOC was formed, this is a small sentence to added over and above Professor Kasim told. When ETSOC was formed, ETSOC got its own vision, but for Kerala, we thought of add a mission to reach that mission. So one of the mission what we thought was improve industry academic interaction. You know why? Even though we have several universities, every year several PhDs coming out with several papers published in IEEE transaction, either in new technology or new products or new services. Very few we could find out commercialized benefiting the society at large. And industry academy has to work together, benefit together, and it should. The academy output is always coming to industry, and industry has to give projects back to academy, fund back to the academy, and both together should develop products. But that I don't say it's not happening, but much less. So this is an area which we thought we will find out from people like Dr. Sukumar, who had exposure to both these places, our places as well as in foreign universities, how better they are performing and what differences it makes for them to perform much better than us. Because it is high time we contribute back to the nation by joining to the industry and academy. And again, India is moving to a condition of more of make in India. Many product technology is getting mapped from China to India. So this is a time where industry academy has to put together, work together, and develop many things. So let us hear from Dr. Sukumar, and let us hear his advice how we can do it better. Thank you, sir.
All right. Thank you, Professor Kasim, for the introduction, and Varghese for introducing me and inviting me for this talk. It's a great honor always to come back and talk to the audience in Kerala because I always I did my undergrad from Kerala, so I always wanted to be associated with whatever the activities which you're doing in Kerala. So it's always an honor to talk to you all on what we are doing and share our experience. So again, thanks for inviting me. And also, thank you all for participating in this discussion today. I'm going to start with some slide presentations and a slide deck with, some specific slides in there. But instead of reading through the slides and then, and then explaining the details in the slide. I will present the slide, and I am going to emphasize on the factors that is required to be mentioned for this talk, and that they are basically my experience on industry interactions, industry related projects. Specifically, I'm going to talk about one project that became a product, and we patented that and introduced to utility in the US, in Charlotte, which is one of the largest utility in the country. And now it is being used fleet-wide, meaning several places in the utility. So the utility has transmission distribution. It's a vertically integrated utility. It has got transmission distribution asset in North Carolina, which is one of the states in the US. They have asset in Florida, is another state in the US, and a couple of other states, Indiana, Ohio. So they have started implementing this product fleet-wide. And I'm going to talk about the internship opportunity we got through that, the project that we developed, product that we developed, field implementation of the product, a company that benefited, a couple of startup company out of it, and students graduated from my lab who is now becoming directors and managers at Duke Energy, which is a utility which I'm talking about, at least 4 of them, and then many others. So I think it's combination of all those things that you were initially discussing about industry-university collaboration, which has happened with this one product, which started as a project in 2013. So with that background, I'm going to start talking through the slide deck about this specific project and product. Can you see my screen and the slides?
Yeah, it is visible.
Yes, sir.
Okay. I'm not able to see the participant list and names there. So if you have any questions, someone has to prompt me or tell me, because I am on a full screen mode, so I am not able to see your face. And also, if you have anything on the chat, we can probably take that later after the talk, right? So,
Sure, sir.
okay, so yeah, so the title that we came up with, rather, we meaning discussing with the Verghese, I came up with this title of Industry Academia Interaction, Success Towards Meaningful Collaboration and Product Development. Again, my name is Sukumar Kamalasadan. I am a professor in the Department of Electrical and Computer Engineering at the University of North Carolina at Charlotte. I'm also associated with a center which is related to power and energy field called Energy Production and Infrastructure Center. And specifically, my name of my lab is Power and Energy and Intelligent System Laboratory, which is under the department and the center. A brief bio about me already has been discussed. I've been associated with the University of Charlotte and then IEEE, Power and Energy Industry Application Societies. My research background, I'm affiliated with several task force and committee meetings with IEEE, especially on power system automation, renewable energy integration, power system oscillation damping control. Mainly started as a power system stability control person, then moved on to modeling, real-time control, DR management integration, and so forth. So PCEL we call it, which is the Power, Energy and Intelligent System Lab. I think the hallmark of this lab, and even at what we do in the center at UNC Charlotte, is that we do applied research. What do you mean by applied research? Is research that benefits the industry and utility. So that's kind of a hallmark for UNC Charlotte. UNC Charlotte is rated the top 5 or 10 in the country for developing new patents and new companies, startup companies. So we do have a center or a place at UNC Charlotte called Incubator Center, where they give space, advice, which is legal, management advices for startup companies. And one of the goals for the university is to economic development, which is basically developing startup companies and helping the university grow along with the professors and students. And I think that is one of the important factor that we should have if we were to have a university industry or academic industry collaboration. I don't know that you do have a lot in Kerala, but that's one of the biggest advantage we have, where university is flexible enough to support new product development, patents, and coming up with a startup company. And we call it graduating that company, where investors can come and then make that company go beyond as a startup. So until that phase, university support that. So having said that, we have in the lab projects related to fundamental research that's supported by a government agency in the US called National Science Foundation. Yeah, most of the fundamental research comes from there. This is based on fundamental sciences. There is another initiative in the US which supports medical research called National Institute of Health, NIH. So for engineering-based work, which is mainly coming from National Science Foundation. And there are agencies in the US, for example, under energy, something called Department of Energy, which is an agency that promote research work that goes beyond fundamental sciences, which means if you want to develop any product at the end of the day and put it in the industry, there are actually 3 phases. The first phase is to come up with idea and come up with the basic modeling methodologies, fundamental theory associated with that idea. That is being supported through this initiative from National Science Foundation. So in the lab, we bring those ideas. We work on the theory. We work on the mainly lab scale experimental prototypes, we call it. So that's what is done in the fundamental science. Now from there, if you want to go to the industry, it has to go through a cycle of improving that lab-based prototype to, we first call it bench scale, then call it field implementable, then call it piloting of that field implementable. Piloting meaning putting that close to product in the field, and the testing in the field, piloting, and then getting the, improving the product. And then finally it becomes a commercial grade kind of product, we call it, which is tested again on the field, then strengthening the commercial grade product to become a, fully usable product. So that's a, kind of phase. So the second phase, which we call it, where taking from the lab prototype to bench scale, piloting it, and then putting that onto the field to test. That part of the research is supported for the energy space through this agency called Department of Energy. So many times the projects die before it becomes a product, and Department of Energy has a curve, or rather a graph that shows that what we call it valley of the death, meaning the project what is being developed in the university will not go beyond the university realm. So this initiative supports that. So in that also there are 2 phases, right? One is basically bench scale, and then developing the bench scale part. So that's basically what we call it as a DOE projects. And then from there, if you want to go to the field testing or piloting, you need to actually have a commercial reason, meaning somebody should get some for-profit commercial reasons. So then only we can have a win-win situation. Somebody should take that initiative, implement it, and test it. Somebody should be able to buy. That part is also supported through National Science Foundation and the Department of Energy through grants called Small Business Initiative Grants. That's where the startup initiative comes into being. It could be a startup or it could be a well-established company, taking that initiative to pilot and test it on the field. So that's done through that. And then it can also be through collaboration by the industry. Industry can provide money, but many times industry may not have that kind of bandwidth to provide money, or also belief in the product. So mostly the small business initiative from these agencies help to support that. So what we have done with this project is we started a little bit backwards. We went directly to Duke Energy and see whether there is a market for a specific project, what we are going to talk about today, which is energy storage, controlling energy storage. So battery energy storage is becoming a very big, or rather coming up as a big item starting from 2010. Now it has got more value because of some initiatives. And why battery energy storage is required? Because of the renewable energy integration to the electric grid. Renewable energy integration is becoming a mandate, and I will show you some slides related to that. And that help to stabilize the renewable energy integration, we need storage. And one of the storage application that has been becoming very useful is battery energy storage. So, but the main challenge of battery energy storage in the power electric distribution system is that it doesn't have a value proposition, meaning it doesn't have a value on how to maximize the benefit of the battery based on the investment that is put in. Why? Because the application that has been used for battery energy storage to support the grid with renewable, we call it grid auxiliary support, which means to suppose you have a voltage fluctuations on the grid, or you have a power imbalance on the grid. How do you balance that? That is the main part of battery energy storage. However, for the electric distribution system, that value is small because the power usage happens there. So the power changes are small, and voltage related aspects is large, but the power imbalance and frequency imbalance is small. So it doesn't have a lot of value proposition. So if you want to really bring up as a value, how do we do? What do we do? That was a question we asked to Duke Energy. And they said, well, that's a great idea. We can provide some support, maybe $50,000, $60,000, which in our case is not that lot of money. So we can do that maybe every year through the state fundings or state help, if you can come up with an idea. So the thought was to see, can we stack services of battery energy storage, multiple services in one architecture? What do you mean by stacking services? For example, suppose you wanted to firm renewable energy output. Firm mean flatten or stabilize the output of photovoltaics. You need battery. So that's one application. Suppose you wanted to shift that energy from one point of time in a day to the next point of time in a day, called energy arbitrage. That's the second application. Can we have multiple of these applications in one control architecture? And battery can do more than one, or one at a different point of time, several ones at different point of time. That was a thought. That can actually improve value for the battery. Otherwise, what was happening was the battery was sitting there idle, collecting dust, not doing anything for some point in the day, or some point in different points in time. So this was the birth of a thought that happened in 2013. And from then on, utility supported this initiative until 2018 or 19 without going to go with the startup companies. And I got supplemental money on fundamental science advances from National Science Foundation and Department of Energy to support that. In 2018, we commercialized that with the help of Duke Energy, and then put that onto the field. So I'm going to go through that journey. These are some of the projects that we do in the lab, fundamental science, like I said, the Duke Energy and the Advance and the Future initiative. So with this specific product, we have two patents, which is fully filed, and 2 professional. We have another product that we are now working with Duke Energy to commercialize that can use battery for different application, which can be working as a UPS on the uninterrupted power supply on the customer side, and the grid auxiliary support on the grid side or the utility side. This technology is called GOPS, GA-UPS, grid auxiliary support and UPS. So that's been patented. We have 2 patents, national and international patent on that one. That is being now being evaluated. So with that, we have 3, full and 3 professional patent associated with that. So with this brief introduction, I'm going to specifically talk about some background and then jump onto that project. So the background, you already know these things, meaning that renewable energy integration is important for low carbon electric grid or low carbon network. Low carbon or no carbon is the mantra for these days, because we wanted to have to go out from fossil fuel support by certain time frame. 2035, basically 2030-35 is in the US, and I don't know about in India, but this 100% renewable integration is one of the requirements by the governments in the countries, different countries, and which also happens in several places. This is electric grid transportation. We are going to go out from gasoline and then or petrol to become no gas electric vehicles. That's another initiative, and how that coupled with the electric grid. So there are different aspects in this, but baseline, you will be not having a lot of fossil fuel generation support for the electric grid. Now, if you don't have that, we have a challenge. The challenge is that the renewable energy generations are what we call it non-dispatchable, meaning if you ask for a 3 megawatt, if you flip a light or switches on your home to turn on power to some appliances or some, and multiple people does that, there is the requirement of some megawatt or some kilowatt. That power has to come from the generator. Generator should have that power to deliver. That such a generator is called dispatchable, meaning it can give you whatever you ask for within its capacity. Now, if the generator says that I don't have a sunlight, so I cannot give you that power, such generators are called non-dispatchable, and that is one important problem related to renewables, right? Because you don't have enough resources for all the time, for example, sunlight. It also has a problem related to not only enough resource, sometimes because of the extra nature, for example, cloud coming in or some, those power outputs are going to be intermittent. Intermittency and variability are 2 different things. Variability happens when the power is not changing very fast. For example, wind is variable, and photovoltaics are considered to be intermittent. So what do you need to do? Well, you need to actually have some backup. You need to have some buffer to smoothen these profile. Otherwise, you will have problems related to frequency regulation or voltage problems or stability related aspects and so forth. So there comes the need for energy storage systems, but energy storage systems are pricey, which means right now I think we are going around $300 to $400, which is very high for a kWh range for battery energy storage with the lithium iron phosphate, for example, is one of the battery that we used for these applications. So battery energy storage are pricey. So how do we use this battery energy storage wisely, meaning with respect to the price that it cost that you incur to buy battery energy storage and the benefit that you can get. So that's basically the main challenge. So if you look at the battery energy storage batteries, so this is actually showing a sketch on how the power electric grid is managed. So if you can look at the lower level, you will have the customers, and then we have the management system on the customers, which is done through electric vehicle, energy management system. Then you have, for example, factory energy management system, home energy management system. You have meter infrastructure that actually gets that information back to the distribution system. Power distribution system, we call it, have a distribution management system, and then community energy management system, and so forth. Now, energy storage, what you call batteries, can be used in the so now after that you have transmission management system, which is energy management system. So batteries can be used at the grid level, bulk grid we call it, at this level, and it can also be used like at your home until at the lower level. On this any level you can use for any size. So that's a great addition to basically improve the reliability and the stability as well as resilience of the power electric grid. So if you want to really look at the operational value for the electric grid, you have to look into both sides of the house, which means you have to look into the transmission electric grid and the distribution electric grid. Many times, because of the jurisdiction and because of where the utility spans, utility may not have visibility probably beyond the distribution grid. So such utility, we call it distribution utility or DISCOs, distribution companies. Some utility are vertically integrated, where you can see the transmission, distribution, and generation all done by one utility. So that was a case which we had. That is kind of a benefit because they can know what are the value proposition. So energy storage application major value of transmission system is frequency regulation, we call it, maintaining the frequency proper by injecting active power. Upgrade deferral for transmission distribution. Upgrade deferral means that you need connecting wires to go from one point to the other point. How do you make sure that these wires should not have to be improved and beyond a course of time? So the conductor wire as well as your current capacity needs to be, conductors has to be reconducted if there is a change in the capacity or requirement in the capacity, which can be deferred by help of energy storage. Spinning reserve, I'm not going to all these. These are kind of applications for energy storage and distribution grid. Voltage step balance, resilience in microgrid, reverse power flow, control of this. So these are the applications, and these are some challenges. Operational value, location and sizing, interconnection issue, management and control, integration to DMS. So what we were looking at was this specific item, which is management and control. So you can see there are more challenges and more things that can be done here, but operational value is important, and the location and sizing as well. So what we wanted to do was we want to be agnostic about the size and the location. Whatever size you say, whatever location you have, can you manage this energy storage? So if you look at the electric distribution grid, for example, on a Duke Energy side, we have a substation, we have a feeder that we call it, which is going into long distance, and it has got a legacy devices called voltage regulators, loads connected, capacitor banks, all that. Now we have renewable energy integrated, solar PV, and then energy storage. So how do you control these solar PV and energy storage? Is basically this box in here that we are. So those controllers are already there. If you wanted to buy an energy storage unit with the multiple batteries connected together using battery energy management system, control architecture is a part of it. The industry, whoever you are buying this energy storage, they will give that. However, they will not give the control architecture that can look into the grid and see what is required for the grid. So that's kind of a supervisory or upper level. That's the control we are talking about. So this is a basic architecture here. You can see that in here, someone has to keep me on check with the time also. If you can, maybe 15 minutes before, if you can mention that, that will be good. Can you help me on that?
Okay,
Time check.
okay.
So this is a stacked energy storage application that I'm talking about, where we have power distribution system, renewable energy capacity firming, energy time shift, voltage support. All these are coming in one control called multifunction control architecture. So what is the value proposition? We will be looking at monetary value of each of these effect on the feeder operation, then I come up with a quantity, which is basically a dollar value. That goes into this control architecture. And the controller will switch between these three or do more than one of these based on this value proposition. Now, what do we need to do this control? We need the sensors information for a legacy controller called voltage regulators, cloud state information, state of charge, to develop an optimization algorithm for this control. And then we also need the PV penetration effect, which actually is projecting the power grid voltages, active and reactive power based on the photovoltaics when photovoltaics happens, right? So, and then we need some information from the feeder. So that's the whole architecture here. Now, what we did then to showcase a business model to the utility, we looked into the value-based energy storage application. You looked into the knowledge that we gathered and then come up with an operational value. Operational value is basically talking about a metric. If this application happens, what will be the goodness of that application from 0 to 1? That's called a metric. And that metric, you convert that into dollar. And that effect we evaluated in the power distribution system. And then for that we need help obviously from the utility. Once we have that economic benefit and reliability measure happens, then we can include that in the application to basically look into what we need to do for your control architecture. So 3-phase: knowledge gathering, then value-based energy storage applications, how you come up with the value. For example, you look into from the knowledge gathered, optimal routine to finding active and reactive power, battery active and reactive power set points, calculate power reference from the PV and the battery power, getting the state of charge and maximum rate of change for the state of charge, providing an optimization parameter for the active power displacement battery, dividing into volt to hour coordination algorithm, and providing reactive power. So you see reactive power and active power both have been supported through this part. And from there, you have a distribution grid model to evaluate it. So this is how the project began as a project phase. Then we evaluated it on the field, tested it on the field, and then we piloted it, basically. So active power capacity is used for PV smoothing and energy arbitrage. Reactive power capacity is used for voltage support and volt-to-hour coordination. If anybody wants to know more about how you get the reactive power capacity from the battery, it's not actually provided by the battery, it is provided by the inverter that is associated with the battery. So you can size the inverter to a higher MVA rating from the megawatt that is required for the active power. So we do have in this project 250 kW battery, 750 kWh capacity, and a 1 MVA inverter. So you have a buffer of around 250, if you look at it that way, on kWh side, where you can utilize if you wanted to do reactive power support. And then we have a load and PV profile optimization routine, which just talks about PV smoothing, energy arbitrage, and voltage support application. So now I'm going to talk a little bit about the technical details. I'm going to go a little bit faster. We can talk about it offline if you have interest. So this is a battery, this is a PV farm, 1 megawatt, 1.25 MVA. And this is a battery, 250, 750 kWh, like I said, connected to an inverter, 1 MVA, on the power distribution network. Both are co-located, which means they are in the same power grid node when we tested it in the utility, and this is a power distribution system. We get the data through a utility message bus. So utility already has this communication or information layer that's done through a message bus, which has got some communication protocol. I'm not going to go in that detail. We can get that info directly at the end, and through Ethernet socket connection with a specific, protection, communication protection, we can get that data in the historic log, and then you can use it for firming reference optimization. That's the first step. So you'll develop a reference, and you get the actual value. Then you put a hard limiter and then changing prioritizing. So this is called value prioritization algorithm. And based on the value prioritization, you can go into 3 applications: energy time shift, voltage support, and the PV station capacity firming. So this is how you generate a reference. So this reference are generated for the photovoltaic without the need for PV forecasting. So that's one, how you reference, what will be the photovoltaic in next period of time. We don't need a PV forecast. We can generate the reference without that. That is one of the good news about this specific approach. So this is a kind of reference that we can generate from the previous data, historical data, for the next last 5 days or last 7 days. So this we call it as a reference. And then you have that reference actually accounted towards in the form of a variable for an objective function minimization architecture. Now, once that reference curve is calculated, you can generate this reference curve. And this is actually the actual value of your power output. With that actual value of that power output, you can create a smoothing reference. So this is actually the real power output in this case. This is output from the battery that is generated to make these outputs smooth. This is basically called smoothing of the photovoltaic. You can smooth the photovoltaic individual asset, or you can also smooth the PCC, which means smooth the output that is injected to the power grid or electric grid. And then what we did, we developed, like I said, a metric called smoothing index. So if you smooth very well, it will get a value which is close to 1. So for example, 0.3 is better, 0.13 is not that great, that kind of thing. So that metric is critical because that metric, calculating that metric is critical because that metric is directly related to the economical value. So this is a kind of summary. So we did 2 methods. In those methods, we can actually have a smoothing index improved from 0.13 to 0.3. 0.3 may not be great, 0.6 maybe, and 1 may be the perfect. So that depends upon the location and size of the battery energy storage. So like I said, we are agnostic about that. We will provide improvement, but how better you can do, if you have money to buy more power battery or higher power battery, you can use that and then improve that from 0.3 to 0.7. That's up to you. So you'll also get that indication of what size is the best size as an outcome of this. Then what we did was we actually improved this beyond the 1 unit and have multiple units. We call it power plant controller. So another solar, another energy storage. If you look at the entire feeder, how can you generate the signal to each of those units, separately? So this is done through a Department of Energy project, which I successfully completed last month. This is called REDIS PV, Optimal Reconfiguration Resilient Control Framework for Real-Time Photovoltaic Dispatch. Like I said, the goal is to support electric grid management system with another management architecture that can deliver power to individual PVs and battery units in the distribution system to maintain the overall health or overall reliability of the power grid. So this is a kind of an architecture which can be coordinated with volt or watt control on the active distribution system. And here is one application. Here you can see that one metric that we use is how you can save the amount of effort on regulators and power distribution system. So regulators, when there is a voltage change, it goes up and down. So this is a number of taps. Whenever it goes up and down, it impacts the life of the regulator. So if you can reduce that tap operation, it improves the life of the regulator. Or sometimes if you can make this operation no change at all, then you can take the regulator out, which means that's asset release. You don't have to put money there for regulator that you can utilize for the battery. So these are kind of things which you can do. Now you can see here the voltage because of that battery unit, which is supplying and absorbing reactive power. It's improved from this red to blue within this band. Another application is voltage profile. Voltage profile is different from voltage band on a regulator point. Profile means voltage across the entire feeder. So you look at different points on in the feeder, and you want to look at the profile everywhere and see how we can improve the profile. What do you mean by improving the profile? To maintain the voltage, we call it 1 per unit or between or close to 1 per unit, which means the outlet you have at your home will have a good quality voltage all the time. It will improve the quality, but not only improve the quality, it will also make sure that the voltage is not going out because of the photovoltaics and other renewable energy resources. We also extended this to a group of the energy storage and photovoltaics in the large utility system to improve the so-called duck curve. So duck curve is something, I don't know whether you've heard of it, is a representation of the output of the total power generated in the entire utility, including renewables. So when you have renewables connected to the utility, your power output because of the renewable will look something like this. So this is like a duck, the shape of a duck, a duck or a hen or whatever some people call it camel also. So it's called duck curve, which means that this power used to be flat if you have a non-dispatchable generating option. But if it's a non-dispatchable generating for renewables, and if it's like only some part of the day you have it, you will see there will be this dip. So now if you're 100% renewable, this is going to be very steep. If this is steep and sometimes go to negative. Now, there are two things which you need to do. It not only steep, it also has fluctuations. So you may want to smoothen the fluctuation, and you may have to lift this to a straight line. And if you do that, then obviously grid is more stable. So how do we do that? And this is actually at the largest level of the grid, meaning at the generating station. So that generating station shape is coming from the local, distributed energy storage and the PVs, right? So what we did was at the local level, can you look at this shape and can you smooth this? So here you see in the green, it is smooth as opposed to this black here. So that's one application. Second application is probably to lift it up. So lifting it up is based on the size. So you can think of how much you need to lift. The problem with not lifting this up is what we call it ramping. Meaning, if you are not able to lift this, when the power grid generation changes, because of the load, you need to rate of change of this generation has to be improved. So that has to be taken care by other generators. So some generators do not have fast ramp up, meaning it will not be able to change so fast. So then it'll not be possible to supply the power. So then there'll be load shedding and associated effect. So that's one. And the second one is maintaining the voltage balance. So you can see this green here is almost like a straight line as opposed to the changing voltages on the other with PV and all. So that's one advantage of this architecture. So you can, on top of that, you can also look into in the form of this as an index. So this is voltage deviation index. Like I said, index calculation and coming up with a metric is critical for value proposition. So ramp rate improvement, power loss improvement, and taps. I talked about all this before. So this is actually the project. Once we developed that project, we tested it in the lab with the help of the microcontroller architecture, deploying that code in the microcontroller architecture. This testing is basically lab prototyping. And after this lab prototyping, we evaluated using the real-time grid simulators in the lab. And then we deployed it into the field with the help of a battery coming from Kokam, actually lithium polymer battery, 250 kW for 3 hours, and photovoltaic inverters, SNC inverter with the sun power, PV system on a medium voltage distribution network. So here is a field. This is a location in Charlotte called Marshall Solar Plant, 1 megawatt, and it's in a feeder called Shirlesford, North Carolina, and battery energy storage system implemented in the field with the help of this controller. Then what we did was we sent the signal through the Ethernet layer to this, and then we tested it on the field, making sure like it's a kind of a call center on 24/7. We need to be here to make sure that the power electric grid utility person as well as a lab. So that's basically one test. And then we deployed this whole control architecture in the field on the pilot study. So that actually, after we did the pilot study, we graduated, said that it's been used for commercial grade and then utilized in the field. So just to summarize, I think I'm still hopefully on time. I wanted to have some interactions and discussions. So just to summarize, The key success for a meaningful collaboration with industry and academia, to me, is to have from the academia side, success is academic project. In this case, was modeling and control of battery energy storage system, understanding challenges and opportunities. Train students to work in this area and provide a workforce development plan so that students can graduate and work in the field. Such projects, if it is successful, it's very good rather, because you have a pipeline now established. To first initiate and establish, obviously, it's very tough. Provide new educational materials that can be used in the classroom, improve your curriculum. All those things are the good news from academic side. Industrial product side, you can showcase the value proposition and key benefit. You should showcase the value proposition and key benefit to the utility. Then only you can get the success, at least to me. And to get support from the industry utilities through financing, field trial, and testing. Sometimes field trial and testing is good. Financing is not possible. So you have to go for government agency support. Financing is good. Field trials are not possible. Then we have to come up with a third-party initiative to do how to do the field trial. And then testing it on the field, utility will say, yeah, you can do all that, but we don't touch our electric grid, because that's basically not allowed. So then you need to have a ways to prove this to apply it. So there are several different levels of challenges. Process include coming up with, so to me, I think to break all this is to have a consensus from the utility and the university to come up with one use case and one market value proposition. Do not talk about several things, and that's just convince that one use case and who can buy this. The only way to implement in industry or the utility is to come up with a monetary benefit. You already know that. Without that, with not for profit or research interest or educational benefit or life benefit, nobody will want to believe that. We need to have some kind of monetary benefit for both. So you need to have an industry or a startup associated with, for example, utility or any other initiative. Other economic drivers, we were able to generate patents, which is good for the university. We can actually extend that to other companies that will improve their profitability. So there is a win-win situation. We have the workforce development part done, and the students graduated work in the utility. So for this initiative, the first student who graduated from my lab, he started looking into battery energy storage propositions for the Duke Energy. Now he is a director of a unit which is originated based on this initiative for microgrids, battery energy storage, and renewable integration, which is, I think, a very nice feeling to have folks graduate and work in the field. So that's another economic driver. Obviously, we have this publications list, which you can look into from maybe my web page as well. I also want to acknowledge the support from Duke Energy for sure, and the National Science Foundation and Department of Energy, national labs. These are actually vehicles of Department of Energy, which will help us collaborate and then bring the project to product. That's another way to do this. And then the university. These are the team members who was notable alums. First 4 are working at Duke Energy. He's the director for that unit, and several others, few others who are collaborated and graduated as alum. So I'm going to stop right here, and maybe we can have some discussions or anything that you wanted to talk about. I hope you are good with the time, right?
Yes, sir. Yes, sir. We have enough time.
So, Dr. Sukumar, it was a nice discussion on the upcoming or current subject, which is very important for the industry. So what I understand was a very highly pain point of industry was addressed by academy, and it was benefited both. I think that would be the right way industry academy interaction can be improved, benefiting both. But it was funded by government or by the industry?
So this project was fully funded by the utility.
No, it was by the industry itself, you can say.
Industry itself. So right from the beginning, it was funded by the industry. Now, 2016, that funding was not enough. Well, industry funding, one of the challenges with the industry funding, at least in here, maybe there too, they have some R&D budget, but it's probably not enough to do everything what we want to do for university. Because university, in our case, we have some kind of a state mandate for supporting infrastructure for the projects, which we call it percentage value for the project. So half of the money goes to the university, basically, whatever we get, which is not a good thing for student support and all that. So I had to seek additional money from government towards the end, like in 2016 onwards, to support multiple people, because this became big, and the utility have not had a lot of money to support. But yes, for 4 years or 5 years, it was fully through industry.
Is there a target for the industry to do so much of a project every year?
So one of the driver in this case was interesting, because industry had a mandate to include renewables in the power distribution system by the government, state government, and the state government has some appropriation money given directly to the utility to support this initiative. So what industry was doing at the third year onwards was to use part of that money to support this project. It supports other projects too. So, but partially that money came to us to support renewable energy integration to the grid. And this technology for the battery was a requirement for industry because they are for profit. So to have something like this for battery energy storage was a kind of value improvement for them. So they had some kind of vested interest there on that part, which is good. And the money which came helped them. So it was kind of win-win scenario. So that's how we could channel. So their benefit, if we can, my experience is their benefit, if we can really narrow down to one specific product and their benefit, their meaning industry benefit, then industry will be a chaperone. They will help work together to channel more money from other resources. So that has happened in this case.
For the research projects in the industry, for the academy, is there any requirement that should benefit industry in the immediate future or anything like that?
So
commercialization.
Yeah, so there are two factors in our case for research. One is the research should drive economic development. That's the main part. Second is research should do education for the students. So any project when comes in research doing education is going to happen in the university. But the research doing economic drive is, I think, one of the things that is good at the US institutes. The economic, improvement is to showcase, maybe you have some startup company in North Carolina, local economic improvement, how economic value happens. So that's a government and the university, mandate basically. So that helped in this case because we could show multiple economic improvement. One is a startup coming out of it, product going to the industry, workforce development, a new unit coming from the industry to the industry based on this, and the new people hired, those based on that. So that was, I think, one of the important point as well. I don't know whether I answered your question correctly.
Yeah, that's okay. This startups comes to the incubators, or they do have some other possibility to do the startup work?
So the startup company, there are three ways the startup initiative happens at the university. One way is to have initiative driven by faculty in students. For example, if I come up with a unit, startup unit, with the help of my students, and then students, university promote that, because that's basically, you can say that is coming from the university itself. That's one way to do. The second way is you have a startup company which is already looking into these areas, which is still a startup, not full scale company, which is located within the university incubator center. So those startup companies taking initiatives of that. The third is utility drive this initiative, and then with the help of collaborating with the university, give this product to a company, maybe a startup or a full-scale company, to promote it further. So all the three options are possible here. In this product, we use the third option, where we went with the utility. We said that this is a utility and university product. Whatever utility we want to do with this product, you can do it. And the utility supported, implemented it on the field fleet-wide, and then delivered to another startup company who can manage that.
You are talking about the death rate of projects, normally how much it is?
75 to 80%.
Oh.
It's very high. It's
Very high.
75 to 80%. Without, if you don't have any, small business funding or government agency initiatives. If you go through small business funding and government agency initiative, the statistics says that we can improve that from 80% to 30%.
That means the startup success rate also is less?
If you don't use the government, support or the university support, yes.
Okay.
So what the startup does is two things. One, what they do is they will know already what the market is, and already find out what we call it as beachhead market, which is one product, one customer. It's called the beachhead, part. So they already know what is the product, what is that market with their experience, and they only go through that product line and then work on it. That's one way. And so venture capitalists or whoever that is, angel funding agencies, they can give the money because they see value, money value, right? X value, multiple X value on that area. The second way is they already know this area, but they don't have money. So they seek agencies like small business initiatives from government agencies to support that. And there is one more way, is that they don't know the beachhead market, one product. So there is last year I attended a government agency project that help find the market. Just for 6 months, they will help us different ways. We do interviews, 100, 200 interviews from different places, and then come up with that one customer, one product market. So that government agencies, otherwise you have to use your personal money or startup money. So if you can line these things carefully, it's a success. There is no doubt about it. But if you don't do that, if you shoot in the dark, or you don't have even data or information to do, then mostly it fails. So that's why this support mechanism helps to improve from 80 to 30%, like I said. On the startup part.
Sir, your session was very interesting. Sir, I would like to ask, what's the role of Department of Energy and National Renewable Energy Lab, that they want to popularize the product in other utilities, or because funding is mainly done by the utility at Charlotte?
For this project you're asking, right?
Yeah.
So this project, Department of Energy is not, so in any case, for that matter, the way the model here in the US is, nobody is going to come to me and give me money for the project. We have to seek with the new technology. Suppose it's here, we have to go and then ask whether there is a need for it or things like that, right? So that's how we have in the US. So we talked to the Duke Energy. So it was just a happen lunch with the manager there, and they said they have an interest, and then discussion went on, and then we got that project, right? Now, once the project is done, so once the project is in the role, I asked for more money because we need to support more, people, and they don't have that more money. So what I did was I wrote a supplemental or request to Department of Energy, like a grant, and then approached the Department of Energy to give me extra money so that I can enhance this product into the, like a higher level scale. There should be a need. They are not going to give this money for same product, right? So that is how the Department of Energy's money came, not for the project I talked about recently, but in general. Is that make sense?
Yes. So I wish to ask a technical question too, like that duck curve you are telling, the belly of the duck curve, how to flatten it up? Maybe is it due by charging the battery or sensing the climate conditions and other things?
Yeah, the same technology. If you wanted to flatten any power curve, you have to send the power or absorb the power, right? That's
Yes.
Only one technology that can send the power and absorb the power is battery.
Yeah.
Because conventional generators, you cannot absorb the power. They only can send. Yeah. So battery, that's why battery is critical for such applications, for sending the power and absorbing. Now, sending the power and absorbing the power can be to smooth the power ripples or power changes, you may call it.
Yeah.
Or it can be to shift the power from one point to the next point, right?
Yeah.
Two different way of. So to shift power from one point to the next point, it's completely related to the size of the battery, right? I mean, you need to have more, power to move. So, but all of them are based on the controls of the battery. Now, to control, you need to know what is the existing scenario, whether you have a ripple there or whether you have a, low, high. That is the knowledge, and so that's the knowledge that we gather. And after you gather that knowledge, then you need to know what to inject, how fast to inject, how much to inject, making sure that the battery is not running out of juice, which is basically the state of charge. That's basically the control, we can call it optimal control or something.
Battery management system takes care of that.
Battery management system will not take care of this. Battery management system is different. Battery management system, what it does is, suppose you have a 250 kW battery, right? As you all know, the battery unit comes with a smaller voltage and smaller power, right?
Yeah.
So many of these batteries stacked together becomes 250 kW.
Yes.
So how to manage the current between all the battery uniformly? That's the first objective of battery management system. What happens if the current is not balanced properly? One battery cell is going to heat up.
Yes.
And one is going to not heat up. And one is going to blow because of its heating up.
Yeah.
So battery management system is not managing that's a misconception. People may not know this or know. The battery management system will not manage the output and input power going in and out from the complete battery stack. It only manages individual cells to operate efficiently, the current, and also making sure that the chemical properties of this, basically based on the temperature, is balanced. So that's the battery man. I don't know whether I answered your question.
Yeah.
So that's a totally different requirement. So if you look at it, there are two different things, right? So we're not touching that box. That box is given by a vendor or a company, right? That company manages that. We don't. So, but you get all the health from that box, right? Like a temperature. You can also get the individual currents in the battery. We also don't manage the state of charge of individual cells. We only look into the state of charge of the entire battery stack, right?
Yeah.
And state of charge of individual cells is maintained by the battery management system. So you understand, right? This is like a smaller level.
If the state of charge of the entire utility battery energy storage system is high, then it should not divert power to battery now.
Yeah, if the state of charge is high, you can take power from the battery and push it to the grid.
Yes,
If the state of charge is low, you have to charge the battery.
Yeah.
So for this kind of application, you may ideally say that the state of charge has to be at the middle, like 50% or whatever.
Yeah.
But that state of charge, whether it should be in the middle or not, is depend upon the time of the day.
Yes.
It depends upon the fluctuations on the power from the renewable energy, right?
Yeah.
So sometimes you may have fluctuations on the power which is only on the positive side, which means you may have to absorb that power.
Yeah.
So how do you know what is the optimal state? That itself is a big problem. It can be a 3-4 year project or so. How do you know what's the optimal battery state of charge? Not the unit, again, the entire battery. You know what I'm talking about, right? The full battery. So that is a kind of one of the things that we are doing in this.
So do we require the battery energy storage system and the solar generation powerhouse, solar generating plant to be co-located, or it could be geospatially distributed?
It can be spatially distributed also. Right now, so there are two smoothing, right? One, if you smooth the photovoltaic, that can be co-located and smooth the photovoltaic output where the battery is sitting along with the photovoltaic. Now, if the battery is sitting on another location, photovoltaic is here, battery will do the smoothing of that point of common coupling, we call it, or PCC for the battery. It may not need to know what the photovoltaic is doing. It can, but the photovoltaic related area may see more harmonics or more fluctuations than this point, where this is because it's another part in the feeder, right? So that, how do you take care of it? That's actually another unit can do, another job.
Another battery should come, rather.
The battery should do or some. So it's not necessary that you should have, and depends on the application. So for example, if you're looking at voltage at the point of coupling, then you need to have something to take care of that voltage. But if you're looking at the voltage profile, then you really don't worry about. So there are key locations, like the electric grid already know key locations, if you operate the electric grid. So one of those locations are voltage regulators. Voltage regulators are placed in the grid depending upon the load in the electric grid. So those locations are critical. That's why you improve the voltage at that point. So if you keep a battery along with the voltage regulator, that's, you don't need any, what is it called, algorithm or anything to understand that. It's normally known. So many of the things are logical you can think of.
Thank you, sir, for the response. Thank you very much.
Sure. Any other comments? Go ahead.
Sir, this is Subish from IIT Madras. Thank you so much for the wonderful presentation. The presentation was so unique and special because you explained the industrial academic interaction with specific examples. So that makes it so special, sir. Thank you so much. And I have one question related to your stating the importance of incubation cells. So from the Indian perspective, what are the lessons which we can learn, or how we can implement it, especially in Kerala, this kind of incubation cells, and above all these kind of models, what are the lessons which we can learn from the US model?
Yeah, so I can talk about the success formula, kind of. I don't know, maybe there is no one formula. It may be different in different places. But what makes a pro-industry academic relation successful, like I was telling, but mainly it is to do with the initiative, what we can bring in locally, for example, in India. I don't know exactly in recent times what are the dynamics and changes there, but I would say a few things which are by and large critical for anywhere in the world to make this kind of initiative successful. First, the academics or the university systems should value this. And for valuing anything for any institution, it should be related to some metric. It could be some monetary benefit, or it could be some success story, or it could be some visibility, or it could be some appreciation. Something of that has to be there. So first point is you should have something like that for the university. So the university in many university may have that or may showcase that. Also, government also should be having that help to the university to develop a center or place called incubation, which can promote the initiatives to go from project to product. So that's the first thing. Number two, university should have a very focused attention on what type of incubation should happen there. So for example, many times I may come up with the idea. It may be hobby idea, and I call it hobby ideas are, I have an idea, but I don't have any fundamental proof or anything like that. Fundamental proof, not mathematically, but some kind of experience related to that. And I'm an individual. I like that idea. University should not, I would think, appreciate that. So for example, when we developed the product in the lab and we were trying to come up for the patent and the incubation, there were 3 levels of meetings and presentations it had. And it also has to happen clearly technically, not related to any other interest. It has to happen at the university level to select what type of products should go into the incubation. That's basically from the university side. And also, what's the economic value? Could it be product, or it could be patent, or it could be students graduating, and that has to be written in record, like 3-year time frame. We have that. That's from the university side. Industry side, industry should be looking at the monetary benefit, like I said, the value proposition, and should help improve that value proposition, discuss with the university and come up with that one. I think the key part is one product, one use, and one value. So if you come with that one number from the industry side, and then industry university should collectively represent to provide, get support from the government or some. If these 3 are thought through properly, with all the 3 parties working together closely, and then I think it's a success model, and it will happen no matter wherever it is done. But we should be careful enough to make sure that everyone is rewarded and everyone values are appreciated, and so nobody has any other vested interest associated in this circle. Just kind of explaining my experience. I'm not, did not write any of these things. I hope that is helpful for you.
So before we proceed with the Q&A session, let us all take a virtual photograph to capture the essence of this event. I would like to request you all to turn your cameras and bring a beautiful smile to your face. I invite Mr. Anandakrishnan, Webmaster, Student Leadership Team 2023, IEEE Education Society Kerala Chapter, to take the picture.
I'm going to take your picture. Done it.
Thank you, Anandakrishnan. Now let us move on to the Q&A session. The participants can either unmute themselves and ask the question or leave it in the chat box.
Yeah, you can ask any questions. No questions are bad. So please, if you have.
Sir, what are some of the potential pitfalls that researchers and industry partners should be aware of when collaborating, and how can these be avoided or managed?
Pitfalls or bad news. So first thing is you should have a common interest or common requirement and a common goal and a common product. So that's the first thing. I think that is required for all the project, but especially for the industry academic collaboration and industry success of the product to be employed or deployed in the industry. You need this. This is the first requirement. For that, you should be understanding the goal from different aspects. Academic goal will be just to develop a project and then give exposure to students or to have them work on a project. That is not going to work in an industry academic success project product relationship, because that project which you are developing or working with the students may not be useful for the industry. So that's what happens every time, most of the time. I have seen several places, unless it's just an educational project. And many times university and the academics do not have that bandwidth or the time to explore beyond that educational development. Beyond meaning, what's the value? Can I do a little bit beyond that? We don't have the time, bandwidth, effort, money, whatever is associated with that. So we should create that first. Should have some mechanism at the institute level to promote that mechanism. In the sense, other resources given to the faculty, equipment like incubation framework, so forth. So that's from the academic side. After that is being taken care, then obviously academics will be more open to discuss this or projects with the industry. So it could be even beyond that. It could be even startup development. We should be able to get some kind of a support from the university for that. Now on the industry side, what you should avoid is supporting a project without having an economic value. So most of the industry will not do that because they are either having money coming or generated within, so they want to know the economic value. But some industry do that because some of the monies are coming from the government agencies. So the industry, what we will do is they will give it to somebody who they know, and they think they can develop a report which may or may not be useful for the industry, but to satisfy the government. That should not happen. If that's the case, then obviously you'll not see any good progress. So with the industry, they have to know the value proposition. For that, the academics has to think outside the box, not just developing something, but also look into whether the value. And the value is not just money. It is also to do with quality of life and other aspects. So if you can write that value proposition down, the industry should appreciate that. Last, very important though, is government support. So the government support, if you wanted to look into, has to come from the value, also come from the economic side of the growth in that area, and support for workforce development, and more important, the willingness from the government. So that industry and academics has to collaborate to showcase. If we do that, then it's successful. But if these things, I don't know which in the priority list, what comes first as the major drawback or setback, I don't know about that, but these things are critical factors.
Thank you.
I guess that is all the questions.
Hello.
Okay, I'm sorry.
Okay. Sir, good evening, sir.
Sure.
I am Dr. Sabina from Chicken College of Engineering. Thank you for the wonderful narration of the way in which the industry academia interaction is happening at your place. In Kerala, the main bottleneck we are facing is this: how to get a good interaction, good industry academy collaboration. And we are doing many projects for industries, but as you said, somewhere it dies. And now the things are changing. And my question is, suppose we are going for a funding with the industry academia collaboration, who will be the first applicant, whether the industry or the academy?
Funding from government, is that what
Yes,
you're
sir, funding agencies.
Okay, so if you're looking for funding agency, the first thing what you have to look into is, at least what we do in the US, is what is the requirement or the vision and mission of that funding agency. That is very important. So several agencies are set up based on to promote several initiatives. So that's their vision and mission. So for example, one agency, it actually is looking at improving startups or coming up with a new company. That's basically the vision of that agency, for example. Then you already know the answer. You should have industry. Maybe industry should be leading along with the academics to promote new initiatives, or academics, if they are leading, they should show the industry backing, so if you go with the idea and then there is no proof that the idea can be tested or verified in an industry setting, it's very likely that, or you don't have experience related to that, it's very likely that this agency may not be appreciable of that. So I would say that before you do who goes with the write-up or who goes as a lead, the zero level is to understand what agency you're applying for and what is the requirement of that agency. And from there, so there are agencies, which is government agencies, which is just looking at, for example, workforce development and giving knowledge to new educational part. Then obviously academics can lead, work on it. I would still think that such projects, without having any real life impact, such projects should be done in a limited way, just maybe for lab exposure or something, should be very limited, and should show the value for the common man, or common so for the society rather. So so I think that could be my answer. I don't know whether
Yes,
you can ask.
Depends on the agency we have to shift. Yeah. Thank you.
I guess that is all the questions we have for today. Thank you so much, sir, for leading this wonderful session. A gentle reminder to the participants that the feedback form will be posted in the chat box soon, and the certificates will be provided solely based on that. So kindly remember to fill it out. As a token of appreciation from our side, we would like to present Dr. Sukumar with a virtual memento. I invite Ms. Anjal Pidiju, V Coordinator, Student Leadership Team 2023, IEEE Education Society Kerala Chapter, to share her screen and present the same.
Thank you.
Any event would be incomplete without the vote of thanks. For gratitude is the ultimation of thankfulness. I would like to invite Engineer M. Anil, Secretary, IEEE Education Society Kerala Chapter, to deliver the vote of thanks.
Thank you, Neha. Good evening, everyone. Good day to the speaker. Respected Chair, IEEE Kerala Section and Founder Chair, IEEE EDSO Kerala Chapter, Professor Muhammad Qasim. Respected guest of the evening, Dr. Sukumar Kamalasadan. Respected IEEE EDSO Kerala Chapter Chair, Engineer CM Vogis. Other dignitaries, my dear friends, ladies and gentlemen. We had a profound speaker this evening, who spoke about the intricacies of industry-academia interaction, with a case project involving development of a project, first translating the project proposal into a product, and then implementing the product for enhancing the service delivery system of a typically vertically integrated utility to create a win-win situation for both the academic institution and the industry. I take this opportunity, sir, to thank you very much for your valuable time, and thank you for the presentation and for the good interaction that you had with the audience. And I thank the chair, Kerala section, for chairing the session. The chair, EDSOC Kerala chapter, CM Bogi sir, for introducing the speaker, and all the participants. Actually, any webinar of this type would not be a success without the audience team. Thank the members of the audience on behalf of IEEE EDSOC Kerala chapters. Finally, a word of thanks again, gratitude to all members of the audience, speakers, and the chair. Thanking you all. Thank you very much. Thank you. Good night.
Thank you. Thank you all. Thank you, Dr. Sukumar.
Thank you.
Thank
See you.
you so much, sir.
Thank you, sir.
With
Thank you.
Thank you so much, sir. With this, we have come to the end of our session. I hope all of you had a great time. I take this opportunity to extend my gratitude once again to the speaker as well as to the participants for making this a success. Do not forget to fill out the feedback form that has been posted in the chat box. And I hope you all have a great weekend ahead and a good night.
We had utilized two Google Meet links to accommodate all the audience. We had 100 plus, maybe 100 and nearly 110 participants for this webinar. It was nice. Thank you.